Okay, so this section has all of one slide to it. And so there's something very simple that we're going to do here. And is we are going to describe how to take benzene and make phenol with it. You're going to have to know a couple steps. Number one, that you've got propene, right? One propene plus phosphoric acid. I doubt this will ever be written out, so you might just memorize the formula for it. Sorry, phosphoric acid, right? And that you get this. You might not have to know that, right? If I gave you benzene and asked you to give me phenol, you could say simply 1, you have to have this stuff. 2, oxygen. 3, acid. And you'd be done, right? You probably, since you're on organic 2, you probably already know that the byproduct we're usually not interested in, right? So in a quiz I might say, effect the following transformation, right? And your answer would be 1, right? Can you see what I'm doing here? 2, O2, and 3, I've got some latency in my pen here, acid, H3O plus, right? That would be the answer in black. I don't think I have anything else to say about this. Acetone is a useful byproduct. We can use it for lots of things. It's used as a solvent. It's used as a cleaner. It's used, I used to use it as a fingernail polish remover, but I think they use something different now in ester. So either way, it's a useful byproduct. So here, yeah, okay, we might be interested in that. Usually, we're not, right? We're not usually interested in anything but the main product of an organic reaction. And then that phenol is used for lots of things, I guess is also important. But the big deal here is the reaction. If I give you benzene, can you make phenol? Like I said down here. Okay, I hope that's helpful. That's section 13.8, lesson 2. All right, so we're into section 13.9 now, and we're back to reactions of alcohols. So we did some reactions before, making alcohols. Now we're doing things that we can do with alcohols, okay? So let's start out here. Let me make sure I got the right color. I got red here, okay. You know what, for mechanisms, I'm gonna go with blue. Okay, yeah. So recall, this is from section 7.5, and we did this before. It's an Sn1 reaction, so watch out for this Sn1, Sn2. It's going to help you categorize these reactions very nicely, okay? So if we have a tertiary alcohol, can you see that here? A tertiary alcohol, right? And what we're not going to do is get backside attack from a nucleophile. That's not going to happen because it's too crowded, right? So what we'll do instead for this reaction, which again we got in section 7.5, this was called, what was it called? Halogenation, I guess, right? I think we called it Sn1 in our list of reactions. I think we simply called it Sn1, a substitution reaction. So what we have is a leaving group here. It's not a very good leaving group though, and it's a common theme in this section, is we're going to make it a good leaving group by protonating it, right? And watch what happens. When that's protonated, what is the leaving group? What is the name of that leaving group? I'll give you a hint. It's an old friend of mine. Water. Can you see that? Okay, so once we protonate this hydroxyl, it becomes water, a leaving group of water. So that's obviously very stable, so that can leave on its own, no problem. Hey, very nice. Okay, now that it's left, we're left with a tertiary carbocation. Tertiary carbocation. Okay? Now with the tertiary carbocation, this is trigonoplanar. Trigonal. I know I'm taking extra time now for this, but I want you to see these words. It's trigonal-planar, which means it's flat and accessible. Can you read my writing? It's flat and accessible. It's trigonal-planar. Okay, and so this bromide comes in on either side. Okay, now if all three of these are the same thing, if they're all methyl groups, it doesn't matter. But if they're three different things, it does matter. You're going to get racemization, right? Because it's not just going to come in on that side, it's also going to come in on the underside. Both, right? Half of them will come in at the top, half the bottom. All right, so that's an SN1. We got that in section 7.5. Do consider going back and looking at that reaction in chapter 7. Especially if it doesn't make sense. If you feel like I have not described that well, go back and read section 7.5 and let's talk about it, okay? That's for tertiary. Doesn't say it here. Where's my pen? Lost my pen. That's for tertiary. Tertiary alcohols. Okay? For primary alcohols, the reaction occurs via SN2. And Klein says also for primary and secondary, it's going to happen SN2. Okay? So here's a primary, because this carbon only has one carbon-carbon bond on it, right? Only has one alkyl group on it. So what happens here is we get, you still get protonation, right? And then you get the generation of a nucleophile, right? So you see this was not a nucleophile before we started. But after I protonate it, why did we protonate this? Why protonate? Can you read this light blue marker? Why protonate? Okay, that's a good question. Now that that's protonated, we have a good leaving group. Okay, and a good nucleophile comes in. Backside attack, and we have a bromine now, right? Now we have the generation of an alkyl halide. Okay, so how's this going to be asked on a quiz or exam? Well, I might say, effect the following transformation, right? Effect the following reaction. That'd be a good way to ask it. Okay? All right, so the first two reactions we got here is an SN1, halogenation, SN1, halogenation, and SN2. Those are the two reactions we got on this page. All right, now the SN2 also occurs with zinc chloride. This is a reaction you did not get in chapter 7. Okay, this is a new reaction. Boom, a new reaction. And what we're doing here is we're using zinc chloride, and that's coming and attacking the zinc. I think if you look in your book, actually I don't have the book in front, well yeah I do, it's right there, but I don't have it open to this right page. I think you're going to find that the mechanism here, you're not required to know it. You're given it here because it helps you understand it. But I think it's not one of the listed mechanisms. So why is this happening? Where am I here? Where's my pen? Why is that happening? Please be ready to answer that. Why is that happening? Okay, now that I've got that on there, I've generated chloride. No, this would be zinc chloride in the presence of other chloride ions, okay? And so what happens now is you have some other chloride that comes in, backside attack, SN2. Do you see the backside attack? And it's concerted, right? This happens at the same time. Backside attack, leaving group leaves. Boom. Gorgeous. Okay? So, in the previous, what's the difference between this reaction and the one on the previous page? Well, the one on the previous page, we were making alkyl bromides, and right here we're making alkyl chlorides. Okay? Now, look at this. Recall from section 7.8 that the hydroxyl group can also be converted into a better leaving group, such as a tosyl group, okay? So, the hydroxide's a bad leaving group. We made it into a good leaving group by adding zinc chloride to it. And we also made it into a good leaving group by adding a proton to it, making it water, right? But another thing we can do is we can add tosyl chloride to it in the presence of a base, in the presence of pyridine. Okay? Any idea what the base is for? What is that base for? Look at the way the reaction is, and you can figure it out. That from here to here, what's missing? Aha, that's why we need the base. Okay? Now that we've got that, we have a good leaving group now. This is a common theme in this section, is making good leaving groups. Now that we've got that, we've got a good leaving group, and we have a nucleophile, aha, that comes in and replaces it. You see here that we've got inversion of configuration, right? Can you see that? This is coming out toward us. This bond is going back behind the paper. Okay, that's inversion of configuration. Look at that word. Inversion. I'm writing this stuff out because when I was a student, my professor of configuration, my first time through organic chemistry, I just didn't hear it. It was just all a bunch of words. Can you see why that's inverted? Okay. So by the way, you notice here we've got a secondary, right? This was a primary, and primaries and secondaries go through Sn2. All right, so now look at this. Thionyl chloride can also be used to convert an alcohol to an alkyl chloride. Again, we've got a bad leaving group. Again, bad leaving group. Hydroxide's a bad leaving group. And here's what we got. I think this mechanism is in your book. It is telling you need to know this one. Go look at that. It's in section 13.9, okay? Look in section 13.9. See if you're supposed to memorize this. All right, now that we've got that, look what happens here. This hydroxyl comes down. Does this look familiar? This looks just like when we had a Grignard reagent attacking a carbonyl. Remember that? You know, gosh, I'm tempted to go back and review that with you. Let's do it. Let's do it. I'm going to keep this. I'm going to go to my whiteboard. Okay. Remember, with our Grignard reagent, we had a carbonyl. We had some alkyl halide, and we treated it with magnesium to make a Grignard reagent. Remember that? Okay. And then this, how many carbons are here, by the way? How many carbons? 1, 2, 3. Believe it or not, sometimes people miscount those, okay? 1, 2, 3. Now that we've got that, this is just like, right? Okay, now this guy comes, boom, attacks him. And that makes remember that? Okay, now here's where it gets tricky. Right, we had 1, 2, 3 carbons, and they're attacking here. So let's watch this. 1, 2, 3. Now, it's so easy. I'm going back to reviewing Grignards right now. So easy to get this wrong. This is by far the most common mistake, is people miscount these carbons. So what am I going to do to avoid miscounting these is I'm going to number them, right? I'm going to number them every time. 1, 2, 3. 1, 2, 3. 1, 2, 3, right? And you might call this, let's say, X and Y. And X and Y are here. That's going to help you avoid miscounting. I would say that's by far, right? That's how you feel when you miscounted. Tears and sweat, right? That's how you feel when you miscount, because it's not necessary. Okay? Don't do this in your head. Make notes for yourself. All right, let's go back. I hope that's not, doesn't feel like a waste for me to take time to draw pictures and have a little bit of, oh, I don't know, I don't want to say fun. It's probably not fun for everybody. All right, let's go back to here now and say, do I have my marker back? Do I have my marker back? No, it's up there, okay. So again, all right, how did I go back to red? I thought I was in blue. All right, so let's go. Can I go back to blue? Sorry, I'm rambling here a little bit. Okay, now does this reaction look familiar? Aha, yes. That looks like my Grignard, right? I have a nucleophile coming in, attacking something. It looks like a carbonyl-carbon. It's not, right? It's a sulfur and an oxygen, but it does exactly the same thing. That's why these mechanisms are important. It'll help you. You'll start to be able to predict what electrons are going to do. So once that goes, you see these electrons now are here, up here, okay? And then they come back down and kick off a chloride. Wow. Chloride's gone. Ah, it's over here, right? Chloride's gone, but the pyridine comes in and takes off. That's the pyridine right there. The pyridine comes in, deprotonates that. This would be a decent leaving group. You see that? We fiddle around this leaving group again. It will be a decent leaving group, but it's not going to leave if it's primary or secondary, right? So we deprotonate this, and then the chloride comes in and boom, kicks it off. Okay, and this leaves. You can see what's going on here. This is a really cool mechanism. I would say probably most of you, maybe all of you, are in a situation such that you're going to need to draw these mechanisms out. You need to copy them out, and you're simply not going to like them until you do that. It's going to seem like a mystery. It's going to seem impossible until you draw them out and memorize them. All right, hopefully these videos are helpful to you. All right, so let's look at another one. Another one is where we've got still a primary, right? Now we come in here, we're making a good leaving group again, right? The hydroxyl electrons come and attack that phosphorus. This is phosphorus tribromide, right? Oops, not di. Phosphorus tribromide. These electrons come in, attack that phosphorus. The bromide gets kicked off, and when it does, the bromide comes in and backside attack. SN2. Wow. I hope this is starting to look familiar to you. If not, it's just because of practice. So I'm going to encourage you to go back and practice it. It's the only way to get to like this stuff. Okay, but it's super predictable. So now what you did was you took this and you made this, right? One propanol, and you made one bromopropane, and this other stuff, which again, I'm going to say is not the main point. I'm oftentimes just going to leave that out when I'm talking about it. Okay? Note that the last step of the thionyl chloride and the phosphorus tribromide mechanisms are SN2. Okay? It might help. It's going to help you actually call these by name. I don't think I'm gonna require it. Phosphorus tribromide, right? But if you call them by name, write them out, and then rehearse them to your study partner, you're gonna get comfortable with this stuff. And when you get comfortable, you're gonna feel like you're good, and that's fun. Okay, now practice with Skill Builder 13.6. Pause the video now and practice that, and come back. Okay, fill in the necessary reagents for the conversions below. Pause the video here. Pause the video here and and draw these out. Okay, I'm going to suppose that you paused it because I told you to. I'm going to suppose you paused it because I told you to. And I'm looking at what I got here in the book. No, these are extra reactions. These are not the ones that are in your skill builder. Okay, so what is this? This reaction, don't try to do this from memory. Really, you should go look at it. This reaction is on page 604. Where am I here? Page 604. Go look at it. This reaction where's that? That reaction, that's going to be closer to the beginning of the chapter, right? Because we're making alcohols, which we did. I think that was the first reaction we did in this chapter. Looking for it right now. Physical properties, that's always the first thing. It's probably section 13.3 where we, is it the first ones we made? Yep, substitution reactions. This one's going to be on page 586. Page 586. Sorry about that. And this reaction is going to be, inversion of configuration, right? You see that? Inversion of configuration. And I'm making a chloride in there. Oh, this is clever. Look at that. I'm about to show you why this is clever. Can you tell me why that's clever? Okay, since we got inversion of configuration, you know it's Sn2, right? So what I'm going to do is I'm going to say that's, oops. I'm going to start to tell you the answer. This is also on page 604. Okay, now why is this clever? It's clever because it's a different question than if I said, watch this. If I said instead, make this stuff. Yeah. Look at that. Oh, wait. Yeah. Look at that. Look at that. See, if I told you to make that from this, then you would do all these steps. But if I told you to go from here, which is still the beginning stuff, call that 1. This is, I don't know, let's call it N. If this is N prime, this is the other stuff, right? Whatever this is, that's the enantiomer of that. Do you see what I'm asking? I'm not sure I asked that question clearly. All right, so this is a separate question. Here's one question. Go from here to here, and the question I asked you just now is go from there to there. I'm not sure that was entirely clear. Come back and ask me about that if you don't like what I've said. My point is we've got clever ways now of getting separate configurations, the different configuration that we want. All right, now let's talk about elimination. In section 8.9, we talked about elimination. We saw that you could take, where am I here? You could take a tertiary alcohol, you see that? 1, 2, 3. And make a good leaving group. Aha, there's my leaving group. What's the name of that leaving group right there? It's an old friend of mine. Love it. I have some right here. So make a good leaving group. After we make the good leaving group, then we take one of these hydrogens. Did you know there's a hydrogen here? Did you know there's another hydrogen here? Did you know there's another one here? Okay, I'm being a little bit absurd now, right? Am I insulting you? Did you know that these are all hydrogens, right? Okay. Sometimes I'll talk to a student and they're like, where'd that hydrogen come from? I'm like, well, there's actually 3 hydrogens on all 3 of these, right? There's a CH3, 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 and there's still 2 more hydrogens here, but we don't draw them all out because we want to keep it simple. So we're just drawing 1, right? This was in section 8.9. This water comes in, abstracts that proton, and these electrons go down and make a double bond. Wow. Cool. Okay. Why is E2 unlikely? You know what? I'm not going to answer this question right now. I really want you to think about that. Why is E2 unlikely? When I ask you to think about these questions, the reason I'm asking it is not because I want to push you harder than you need to be pushed. It is because thinking about these things will help you understand it more deeply. And when you understand it, then it's less memorization, right? It's more, hey, I get it, okay? It's like speaking a language. Instead of memorizing a bunch of unintelligible syllables, we start to understand what's being said. Okay? Recall that the reaction generally produces more substituted alkene product, right? So how many substituents does that double bond have, and how many substituents does that double bond have? All right, I think that's it. I'm going to ask you one more question here. If the alcohol is converted into a better leaving group, oh, no, that's not it. Here's some more facts, right? If the alcohol is converted to a better leaving group, then a strong base can be used to promote E2. Right? So before, on the previous page, we had E1, and it was not going to go this way. This acid-catalyzed elimination was not going to go E2. Why? And that's what my question was here. Why? Okay, but if we make a good leaving group, and this is in base. You see that? There's my base. If this is in base, make a good leaving group, and then we have a really strong base, sodium ethoxide, which is that, right? There's a minus on here. And then sodium, of course, is just a spectator ion. It's someplace else. So when you're drawing this out, you don't even see that. That's what you see. Ethoxide, that comes in as a base. What does that base do? Well, you're told what the product is, right? And so I'm going to encourage you, go back to chapter, I think that's chapter 8, and look at what that mechanism is. This is an important mechanism. You need it. It's going to help you. It's going to help you. Okay, E2 reactions do not involve rearrangements. Wow, another good question. Why? Why is that? Gosh, I don't want to answer that for you. I think it's going to help you if you think about that. All right, I know it's going to. You could look it up probably. All right, either way, you're going to get that better than if I just tell you. So you ask me in class if you've tried or if you've lost your spirit. Okay, when applicable, E2 reactions also produce the more substituted product. Okay, let me say nothing about that right now. Leave it up to you. Practice with conceptual checkpoint 13.21. And I think that's it.